ladies and gentlemen. I would like to begin by expressing my sincere gratitude to Ventsim User Conference for extending me the invitation to speak today. This event serves as an important platform to exchange ideas and share knowledge. I hope I could also contribute to the dialogue today. I will do my best to deliver a presentation that meets your expectations, and so I hope that the insights shared here today will be valuable to each one of you. Thank you, and let's begin. The agenda for this presentation starts with a brief description of the mining activity in the Andes, given that the case study is located in Peru, followed by the general consideration for current mine ventilation system design. Then we will review the initial parameters from the pre-feasibility study of the project, so we can discuss all feedings of optimization work prepared for the feasibility stage, closing with the results, life of mine simulation, and final conclusions. Peru is one of the mega-diverse countries in America due to the diversity of the climatic conditions. The location of the country within the Andes mountain range is the reason of the abundant mineral deposits. From 87 mining operations, 41 are operated through underground methods. From the 41 activity underground methods, 3 are at sea level, 8 at medium elevation, 6 about 3,000 meters above sea level, and 14 over 4,500 meters above sea level. The coastal region has a typical dry climate with high temperatures. The highlands located within the Andes are cold, while the Amazon region is humid with a mild weather. This environmental diversity has a direct impact on the power consumption by the ventilation system due to the change in the air density, further affected by local weather conditions, making it difficult to compare mines even at the same elevation with different environmental parameters. As a reminder, modern ventilation systems have 3 stages: the construction of the model to create a representative of the geometry of the mine, the calibration to adjust the associated resistance in the system and the environmental conditions, and finally, the simulation of alternative conditions to evaluate potential scenarios and outcomes. Let's review the starting point of the study. The details of the base case are elevation with respect to the sea level, current depth, and projected depth. To be able to find any opportunity for improvement, we must understand the initial proposed ventilation system first. From the initial view, I ensure that the specialists among the public may have already identified some deficiencies in the system. Let's discuss the details next. The pre-feasibility ventilation system makes use of the existing infrastructure to define a fresh air intake circuits towards the lower levels. Apparently, this arrangement is convenient to the purpose of the production target. However, we must evaluate the ventilation from the big picture to guarantee an adequate exhaust circuit. Having this type of intake system usually generates ventilation deficiencies in other parts of the mine, because adequate airflow is required everywhere in the mine and not just in the production zones. From the exhaust circuit standpoint, we may take into consideration additional parameters, such as the commercial ability of funds. The optimization of the exhaust circuit is required from the beginning of the mine operation, and it turns into a recurrent process. We can observe a high airflow in the exhaust circuit through 2 ventilation races, with expected capacity of 600,000 CFM, with a power consumption up to 2,000 HP in each race. Because of this, even under similar environmental conditions, there was no previous experience in any mine in Peru with such level of power consumption and equipment, generating additional costs for the implementing and expected operating of the proposed system. Another identified opportunity for the improvement of the proposed use of access tunnel with the shortest distance to the production zone as an exhaust circuit. This alternative have two shortcomings. First, using a long distance and high resistance airway as an exhaust circuit is reflected in a high pressure and low airflow system. Second, it dismisses the use of direct evacuation routes for the workers in the lower levels in case of mine fire. We are talking about 3.4 kilometers in horizontal distance compared to that current 5 kilometers evacuation route. Another relevant aspect of the design of a simulation model is the density associated with the dry and wet bulb temperatures on surface and the barometric pressure at the site. The initial model, we observed that the barometric pressure was adequately estimated to the elevation of the mine, but the assumption for the dry and wet bulb temperatures may be not accurate, because at the elevation we may expect much lower temperatures during most of the year. On the other hand, we expect friction factors were proposed based on bibliographic reference without taking into consideration other information sources, such as similar mining operations or even from the mine itself. As we know, the airflow requirements are key to establish the capacity of the system, adding the conditions that, in accordance with the Peruvian mining law, we must include an extra 15% of the overall airflow requirements to cover any leak, resulting in an overestimating system reflects in around 50% additional power consumption. Given that the hauling system will be trucks, the associated airflow requirements will play a major role in the overall requirements, complemented with the airflow required by the sculpture and pickup trucks. Originally, the pre-feasibility study estimates an overall capex to develop mine ventilation infrastructure of $23 million, with an associated NPV of the OPEX over the life of mine of $11 million at 12% annual rate of return. As expected before, some environmental conditions were different than what was assumed in the pre-feasibility study, confirming that some adjustments were need to be made. Now that we have the baseline information, we can start discussing the findings that will modify the project. Upon completing the environmental conditions monitoring on surface, we detect a clear correlation between the dry and wet bulb temperatures, specific for the site. From the chart, we can observe an inversely proportional relationship between the dry bulb and humidity levels, with the relative humidity below 70% most of the year. The highest temperature at daylight is 16 Celsius degree at 39% humidity, while the lowest temperature is about 2 Celsius degree at 66% humidity. This information is relevant to the model, and it defines the baseline air conditions for the simulation stage. From the monitoring data, a new configuration for the Ventsim model was evaluated using the average of the night conditions as representative values. This resulted in an increment of 14% of the air density, impacting in the previously estimated power consumption. The color legend tool in Ventsim is convenient when we need to differentiate the characteristic parameters of the airways, especially in big models where we group airways based on certain parameters. So we can easily identify, for example, the different friction factors assigned to each airway and to evaluate if the airway configuration was correctly done. Regarding the yearly airflow requirements, we can observe that the highest value in the pre-feasibility estimation, 1.38 million CFN, was updated and reduced to 1.28 million CFN, representing a decrease of 7.6% and resulting in a reduction of the power consumption of 20%, having a positive impact on the NPV of the project. One major component was, in fact, the reevaluation of the existing and proposed infrastructure. During the feasibility study assessment, based on the new conditions evaluated, a new strategy is proposed to improve the main ventilation system design from the feasibility study. This strategy is based in 3 core ideas: develop a gap analysis to identify opportunities for improvement based on the efficiency of the base model and guarantee adequate evacuation routes in the case of mine fire. Second, reconfigure the ventilation circuit, preventing the saturation of airflow in small areas. And lastly, reuse of the existing infrastructure, complementing the reconfiguration of the airflow circuits to ensure the ventilation coverage and prevent recirculation. In the analysis of each of these components, the Ventsim was the utmost important to ease the identification and evaluation of the impact of the implemented change. Based on this strategy, we propose to evaluate complementary alternatives to improve the airflow distributions and to prevent concentrating oil resistance onto just rays. For this, it's important to consider that a 10% decrease on the airflow represents savings up to 27% on the power consumption in accordance to the square cube law. Upon the verification of the available infrastructure, we evaluate that the ventilation circuit B will provide enough operational and safety considerations and circuit continuity to be repurposed to long term. Finally, using the simulation tools from Ventsim, we identified that a decrease of 70% in the airflow of the circuit C and D would generate a reduction of up to 42% of the power consumption in each fan. The airflow variation was redirected to the circuit B, balancing the total airflow and standardizing the nominal power of the fans, having a direct impact on the acquisition cost. Following the geomechanical considerations, a resizing of the bottleneck airway is proposed to allow a reduction in the power consumption generated by this segment of the circuit by using the linear statistic tool from Ventsim. we could verify the power consumption reduction and the corresponding economic benefits. Another improvement was the reuse of a former exhaust circuit into a evacuation route for the existing and future production areas of the mine, so we could guarantee a short, safe escape wave for a greater number of workers in case of mine fire. The other point of discussion was the correct setup of the mine funds. From the identified opportunities for improvement and the tool provided by Ventsim, we could verify that an adequate reconfiguration of the ventilation circuit would result in typical operating points, similar to other mines in Peru, preventing overestimated CAPEX and OPEX related costs in the mine ventilation system. Finally, we can observe how the proposed implementations allow a standardization of airflow capacity and required power of the equipment for the mine ventilation system, resulting in operating, logistic, and maintenance advantage, as the spare parts and related procedures can be easily integrated to the planning process. From the economic standpoint, we can see the impact of the proposed alternative in the CAPEX of the ventilation system, which a significant decrease of almost $10 million, mostly related to the standardization of the mine fines required by the system. The impact is also on the operating costs due to the decrease of the power consumption, reducing the estimated OPEX NPV in $4 million, making total savings of $14 million. Once we had the new model fully calibrated and the long-term mine plans, we were ready to simulate the ventilation system for the life of mine. Lastly, the stage V tool in Ventsim was one of the most useful resources when evaluating the medium and long-term ventilation design. For this, the construction of the model must consider an adequate integration between stages, making them depend between each other, so that is there modifying in early stages. It must be reflected in the following stages in case it is required. If we can achieve this, we could provide in-depth analysis of the evolution of the system and the characteristic parameters, allowing the identification of new opportunities for improvement not only the ventilation system, but also in the development and production sequencing, resulting in overall better working conditions and the optimization of the cost effectiveness of the mine. Conclusions. Ventsim comes handy in the construction of the ventilation models and sequence calibration with respect to the project upon completing the economic assessment of the initial design against the proposed new system. There were significant savings in the CAPEX and OPEX of the project. Lastly, having the possibility to plan ahead and simulate multiple scenarios of the mine gives us an idea of what is best for the operating and the initial stages, and what modifications should be applied over the life of mine. About the pending tasks, there is still work to do in the project, especially in the mine, fire simulation, and heat analysis. Thank you, and I will be happy to answer any question you may have.
Thank you for your time. Any questions? There you go.
Thank you, Daniel. A good presentation. Just a more general question there. You know, I mean, it's pretty, I guess, surprising to see, you know, these very low barometric pressure and low densities, right? I mean, we're not used to deal with that here. And I guess as a general question there, in terms of mine ventilation, what is your biggest challenge there with respect, you know, to keeping the workers safe in such low density environment? You know, do you have any issues, let's say, with diesel equipment, you know, emitting more contaminants, or are there any other challenges, obviously, with the fans and anything else?
Okay, thank you for your question. The principal challenge in high altitude mines maybe is the quality selection of the fan, because you select the mine fan for the highest level of the mine, and maybe for a low air density. But when you talk about the auxiliary or front fans or the blink works, you are talking about workings in the low levels of the mine, and the change in density is very important. Maybe this is the principal challenge for the ventilation engineers in Peru. Differentiate when a fan is working in the high levels and when a fan is working in the lower levels.
Thank you.
Okay, thank you.
Okay, any other questions?
Hi. Again, great presentation. Just a topic of interest for myself, out of curiosity, seeing the staging for the life of mine plan is something that our group at Valley does quite regularly, and I guess we'll actually have a couple of presentations about that in the near future. But out of curiosity, for your life of mine account for air determination, how is it that your group particularly addresses that to get yearly flows or yearly quantities for the mine as a whole?
Okay, thank you so much. Maybe the yearly estimation of the airflow responds to the mine planning, because if the mine planning is not stable, we have different change in the requirement of equipment for the production. Because of that, we try to analyze these different variations yearly by yearly in the airflow demand. Definitely, I think the design is for the worst conditions, but maybe the worst condition is not in the first year or in the middle year. Maybe because the main planning is variable, the worst year maybe is in the middle or in the last years. Because of that, we analyze the airflow for the yearly to identify when is the maximum demand of the air to design or to select the main fan in function of these stages. Okay, thank you.
Great. Thank you, everyone.